I'm armed with a marker and an eraser. We're going to get going right down these RF properties. Now, this isn't all of them. Some of them required a little more special attention, so if you feel like this is missing something, check the other videos. So first, we're just going to knock these out. Attenuation is loss. So as light, if you were to shine a flashlight, it doesn't go forever. It loses energy. Well, that's actually not technically true. The energy gets dispersed to where it's not effective anymore. This is actually done in what's called the inverse square law, which is a really complicated way to say that as light or signal or anything starts to go out from its source, that it gets dispersed in some sort of a pattern that looks like this. This is our antenna here, that it goes out like this. And as that happens, if you were to measure the signal right here, it's much stronger if you measure it here because that same energy has been dispersed. Now, some rules that go along with that. For every time you double the distance, you lose 6 decibels. Now, what's a decibel? We haven't gotten to that part yet, but just know that it is a unit of energy. So basically, if you start with, let's say you start right here and you measure 10 as your signal, that when you lose 6 decibels, you're going to end up with 2.5. 10 what, 2.5 what, doesn't matter yet. So when you measure signal, again, as you lose that, again, let's pretend we lose that 6 decibels here, we end up with 2.5. So that is attenuation, has no obstacles, no nothing, it's just general attenuation. The next is the opposite, amplification. We want to get more signal. First thing to know, the only way to add signal is by adding power. There's no way to add signal passively. A lot of people think an antenna adds signal. They don't. They do something totally different, which is, as you guessed it, another video. Amplification is gain. It is actually something called an amplifier. An amplifier would have, you could say your access point, your transmitter is here, connected to the input, and on the way out, it has more signal. It amplifies that signal, and this is actually a powered device. So this would have electricity powering that amplifier in order to get that gain that we're looking for. In Wi-Fi, these are actually not used very often anymore. I used to use them a lot 10, 12 years ago when I was trying to do really long distance shots. Today, you don't really need to do that. I'm not saying you'll never see them, but just know that these are definitely not something you're going to run to the store and get and use every day. Another RF property, absorption. This seems pretty simple. If you have light going into a black cloth, where does it go? It absorbs it. What happens when signal goes through drywall? It absorbs it. Part of it, not all of it. So absorption is just, we could take a drywall, and as signal goes in, let's say it goes in at a signal level, a real signal level, say negative 60 dBm. Again, we haven't got to the dBm part yet. Don't worry about it too much. That when it exits the other side, it may be negative 64 dBm. Maybe this drywall has a 4 decibel loss. Problem with classes like this and courses like this is it's a catch-22. Which do you teach first? Well, teaching decibels right up front may be a little scary, so we tend to kind of move that on once we learn this. So don't worry about this too much. If this is confusing, maybe come back to this after the power measurement section. But just real simple, something that loses more signal going through it, a lot of that can be due to absorption. Another RF property is reflection, probably one of the simplest ones to understand. We have some sort of an object. Typically, you're not going to see it being, it actually could be absorbing and reflecting at the same time. That's actually fairly typical. Signal comes in and hits it, just like light with a mirror, it bounces back. Now, some of it may be absorbed, some of it may go through, and some of it may be reflected. So don't think that it's just one property that every signal must follow. Signal goes in, signal bounces off, reflection. Scattering is just multiple reflections. I don't know a great example of this. Let's say you have rocks. I don't know why you'd be shooting signal into rocks, but let's just say you do. You have some sort of rocks formation. You got to do something here, right? Signal hits that rock formation. What is going to happen? Multiple little reflections. We call that scattering. Now, I'm sure that those of you watching this are of varying age ranges. I'm under 40, let's just call it that. And I remember that growing up, people would have the prisms hanging from their mirror, the little crystals. And what you would see is that when light would go into it, you'd get a whole bunch of little tiny beams of light coming out of it. That's called refraction. The signal goes into something, some object, signal goes in, and when it comes out, it may be coming out a different direction. Maybe it's multiple different directions. Maybe even get a little bit of reflection in there. Again, keep in mind, there's rarely something that will just do one of these things up here. Most of the time, it's a combination. But refraction is the signal going in at one angle, coming out at another. The last is diffraction. If you think back to the last time you spent any time in a pool or a lake, diffraction happens all the time. So if you have, let's say, a rock or yourself in the water, and maybe waves are coming at you, and what you'll see is the waves kind of curve around you, and then they actually curve around and kind of keep going again. Diffraction is, now imagine this is signal instead of water. The signal hits this object, and the waves are rippling to it, and then ripple around it and keep going. Diffraction can also be shown like this. Let's say you have a hard-edged building, or in real life, I've seen this in a mountaintop. Signal, let's call this a mountain right now. Signal shooting up the side of this will actually curve at the top. There's actually uses for this. Now, this is not really a Wi-Fi use case. This is more something you'll see in lower frequencies. But let's look at the opposite. Maybe there's a transmitter on top of the mountain, and as it goes out, it'll actually curve around. These are used in real life on purpose. That curvature around an object is called diffraction. Hopefully this helps explain these 7 RF properties, and I think gives us a good base to keep moving on.